At first, it was an infinitely dense matter mass. This mass went through an explosion that resulted in the creation of molecules, atoms, stars, and galaxies that can be observed right now. This has been the reasoning provided by physicists for decades, but a new idea has emerged from recent research. A vantage point suggests that the universe does not have as early an origin as originally thought. Instead, it may be part of a cyclical process in which the universe experiences a sequence of expansion and contraction cycles. Brian Cox, a renowned physicist, has also raised doubts about the Big Bang theory, arguing that it cannot result in anything from nothing. This inquiry adds a fascinating aspect to the discussion. In addition, research from the James Webb Telescope has provided information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang did not mark the beginning of the universe, what did? Take this journey with us to the beginnings of the cosmos, where we will explore the Big Bang's frontiers and respond to this question and numerous others. If you want to keep up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to expand its audience, and turn on the notification bell. Scientists have developed a thorough comprehension of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is in the recent past, about 13.8 billion years ago. During that period, all of our world's constituent parts were formed in a matter of minutes. In this theory about the universe, which includes stars and galaxies, it once weighed as little as a peach and had an extremely high temperature of more than a quadrillion degrees. This astonishing narrative aligns consistently with all current observations made by astronomers. They have investigated everything from the remnant electromagnetic radiation of the early universe to the abundance of the smallest components, and have discovered that the predictions of the Big Bang are correct in every way. To the best of our knowledge, this description fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the Big Bang theory is not the complete picture. The missing piece in this puzzle is an understanding of the first moments of the universe. This challenge is largely due to the limitations of the physical theories we currently employ. The combination of general relativity and the physics of high-energy particles gives us an important conceptual framework. However, as we delve deeper into the very beginning of the universe, the mathematical complexity increases significantly, reaching a point at which our current methods are unable to provide meaningful solutions. One example of this problem is the existence of a singularity, a point at the beginning of the Big Bang with infinite density. This idea implies that the universe was once compressed into a state that is infinitely small and dense, which appears absurd. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provide a more comprehensive understanding of the first instance of the universe. Our current instruments and theoretical frameworks are not robust enough to solve this problem. We must therefore develop new physics that can encompass and explain gravity and the other fundamental forces at very high energies. This is where string theory comes into the picture. This theory aspires to be a physical model capable of unifying gravity with the other fundamental forces, particularly at ultra-high energies. In essence, string theory posits that it can provide an explanation for the first moments of the universe. The universe, as explained by string theory, introduces the idea of an ekpyrotic universe, which takes its name from the Greek word meaning conflagration or fire. This idea suggests that the Big Bang, in its current form, was the result of an earlier event, implying that it was not the absolute beginning, but rather a part of an ongoing process. Introducing the concept of an ekpyrotic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for millennia, string theory provides a solid mathematical basis for this conception. In the context of cyclic cosmology, The universe operates as though it exists forever, oscillating between large explosions and ruining itself in a vicious cycle that extends into the past indefinitely and into the future. This cyclic cosmology theory was suggested by the renowned physicist Roger Penrose, who won the Nobel Prize. Penrose was intrigued by an amazing mathematical connection between the early universe, defined by its extreme compactness, heat, and density during the Big Bang, and the future state of the universe, distinguished as extremely cold, expanded, and without matter. According to the theory, these two states are mathematically transformed, identical when tested to the breaking point. Even though it may appear contradictory, the total absence of matter could be the driving force behind the creation of all the stuff we see around us in the universe. From this vantage point, the Big Bang originates from what almost remains imperceptibly after all the matter in black holes has completely consumed the universe, leaving a vast void filled with scattered photons. The universe emerges from what, from another perspective, basically approaches nothingness, despite the fact that this nothingness is a form of something that resembles a real universe, albeit an empty one. The method by which the same state can be seen as both a dense universe and a cold, empty universe is based on perspective. Important to this comprehension is a complicated method in mathematics known as a form of conformal transformation, a geometric transformation that changes the size of an object while retaining its form. Roger Penrose demonstrated that the cold, empty state and the hot, dense state can be linked together by this scale transformation, aligning their spatiotemporal structures despite their variations in size. They may be essentially the same, despite having different sizes. However, Penrose argues that the concept of size loses its significance in light of these extreme physical circumstances. In cyclic cosmology, a sequence of events unfolds from an old, cold state to a young, hot state. The hot and dense state is caused by the previous cold and empty state, but this causal relationship does not follow the usual pattern in terms of time. Since, in these extreme states, both time and size lose their traditional meanings, the cold, empty state and the hot, dense state exist on distinct timelines. This indicates that, from the perspective of an observer in their own time, the cold, empty state would continue indefinitely. Philosophy and physics go hand in hand in this realm of cyclic concepts. The study of the cosmos offers speculative and detailed explanations for the origin of these cycles. However, even if Penrose's cosmology lends credence to these ideas, a more in-depth philosophical question still hasn't been answered. Where did the actual physical reality of these cycles come from? This brings us to ponder the reason for the existence of something as opposed to nothing, a fundamental metaphysical question. For our purposes of discussion, we will focus on explanations within the realm of physics. There are three possibilities to consider when looking at the very beginnings of these cycles. First, there may be no physical explanation at all. Second, there could be an infinite series of cycles in which each cycle is a different universe, and the quantum state of each universe is somehow determined by some aspect of the universe before it. Finally, there is the option of a single cycle, in a universe that continues from where it began. The cycle is explained by some feature of its own end. These opportunities are appealing because they steer clear of unforeseen occurrences and offer a more in-depth explanation within the framework of the physical realm of physics. Penrose proposes the idea of an endless sequence of cycles, influenced by his interpretation of quantum mechanics. In the study of quantum mechanics, a physical system is made up of several states concurrently until it is observed, at which point it collapses randomly into a single state. Penrose suggests that each cycle is influenced by erratic quantum events that result in variations between cycles. This idea opens up promising opportunities for experimental physicists because it suggests the possibility of detecting anomalies or subtle traces in the remnant radiation of the Big Bang.